还没到啊。
出错率其实，
那你们刚刚是报什么？
像是这样子，
什么 disc 的东西？
第一个，
disc
通常
4号，
第一个吧，
说 hydroponic
其他几种语言呢，法文啊，
各个语言是独立的。
其实最好，比如说法国人当然看法文是最主要，荷兰人看荷兰文，一般来讲是这样，可是有时候很难。但是英文、中文太多错误，又超级错误的拿出来。连他妈妈都提早10年死掉了，碰不起来，怎么？
他是说把水柱冲到那个洞里面，然后那个圆盘会飘起来，这样吗？
我都看他的那个影片，
是这样吗？
他就是哇，然后那个东西就一根浮着这样。
你说他往那个中间那个灌。
哦，加中火。那个是912什么意思？
有时候打100个，
跳
可是听说有人验证过打100个是不能
好像有9颗啊，对啊，感觉蛮可的。
原点当然最好，可是原点很多。
没有，我觉得刚刚
不是我们语言的，那也就算了，你很难直接
什么我都忘记了。
来 copy paste 的，
叫。
要不是有找到原文哇，我要去看法文，是不是很旧的那种
英文超，
你就把它
看英文超强。
哦 ，Tesla。Tesla 那边好可惜。为什么你有饼干？
等一下有，现在有。
对，然后就下去。
前一天的我们2个世界对话录从来没看过翻译。你在网络上可以看到结义，它
Okay, let's start the second round of this one. I'll ask the opponent to pick a problem to challenge the reporter. Okay, 1 minute.
We would like to challenge number 10 draw athletics.
Number 10. Okay, problem number 10. Okay, wait. Okay. Now, each team please write down your presenter full names on the blackboard.
Okay, so hello everyone. We're Team Tesla from Pingdong High School, and today we're going to present droplet explosion. Okay, this is our introduction to the test. When the drop of the water mixture, for example, water plus alcohol, is deposited on the surface of a hydrophobic liquid, like a vegetable oil, the resulting drop may sometimes fragment into smaller droplets. Investigate the parameters that affect the fragmentation and the size of the final droplets. Okay, and this is our experiment. First, we use a dropper to drop the water-alcohol mixture on the oil surface, and we use camera to observe the phenomena. Okay, and this is our observation. First, the drop, we dye the mixture in red, and it will spread out in two circles, which this is the smaller one, and the outer one is the bigger one. And during the spread, it will fragment into small droplets. Okay. Okay. So we define the smaller circle here as R, as radius, and so why does the droplet spread out and fragment into smaller droplets? Okay, first we want to introduce the properties of the fluids. First, as the test mentioned, we use sunflower oil as the vegetable oil, and water, and of course, ethanol. And we want to show here is that the sunflower's density is between the water and the ethanol, and this is important to this experiment. And so the sunflower oil's dynamic viscosity, which represents its thickness, is much more higher than water and ethanol. And the surface tension of water is much higher than ethanol and sunflower oil. And I want to talk more about this part, the density part. When we only use water to drop on the sunflower oil, it will sink in the bottom of the oil. And if we use only ethanol, it will spread out, and we cannot observe the phenomena. It's just spreads out too fast. Okay, so we divide this phenomenon into two parts. First, the liquid flows outward, and how does the droplet fragments into smaller droplet? Okay, this is our first part. Okay, the evaporation of alcohol at edge is most efficient because it just spreads from the inner side to the outer. So the surface tension of water is higher than that of the alcohol, so that these in the inside will have a lower surface tension, while the outer side will have a higher one. So thus the liquid flows outward. This is our second part. Liquid flows outward, and then liquid gather at the edge, and then droplet fragment into smaller droplet. As we see here, this is the original droplet. While it spreads out, it will gather at the edge, and then become smaller and smaller droplets, and this is the sunflower oil. Okay, and in the test, it mentioned that there are some limits of this phenomena. So we have to find the limit of that droplet must float on surface. So law of A is the density of ethanol, and law of W is the water's density. And basically, the left-hand side of the inequality has to be smaller than low oil, which represents the oil's density, and thus this we can observe the phenomena. So here, alpha, which represents the concentration of water mixture, has to be bigger than the right-hand side of the inequality. Okay, so in our experiment, we use the inequality on the previous page to determine which alpha is necessary to observe the phenomena. And we find out that alpha has to be bigger than about 32.74%. So the minimum concentration of alcohol has to be 32.74%. Here's our data. First, the x-axis is time, and the y-axis is radius. As I mentioned, this is the radius of the smaller circle. And here are some different concentration of the mixture. And we define that the end of the phenomena is T end, like here. And the highest point of the radius of inner side is R of max, R max. Okay. And so we see here the higher the mixture is, the higher concentration the mixture is, the more time it will become. Okay. And here's our concentration versus R max, as we mentioned here, R max. Okay, and we find out that this is a linear thing, like the x-axis and y-axis. The more the concentration, the bigger the radius of the inner circle. And this is another graph of concentration and T end. As we mentioned, the higher the concentration, the higher the time, the T end. Okay, and we've drawn these graphs on the previous pages on one graph, and we find out that this is a parabola, while the x-axis is T over T end, which you can say that represents the percentage of time at each point, and this one is R over R max, which you can say it represents the percentage of radius, of the maximum radius over time. Okay, so this is the difference from these two. Okay, so because this is a parabola, we find out this equation, and so when T over Tn is equal to 0, R over R max is equal to 0. So we put that into our equation, and we find that K is -4. So we wrote the equation again, and we find out that this equation R equals to R max times the right hand side of the equation. Okay. Here's our conclusion. First, the evaporation of alcohol and the difference of surface tension cause this phenomenon. And second, the concentration of water mixture in our experiment alpha, it has to be bigger than 32.74% so that we can observe the phenomenon. And third, while concentration goes up, the R max and Tn both go up, and it's linear. And we find out this equation here, which represents the R of each different concentration versus the R max here. All right, thanks for watching our presentation. Thank you.
Okay, thank you. So, short question from the opponent, please.
Okay. In your experiments, have you considered using different alcohol and oil types? For example, for alcohol, isopropyl, or ethanol or methanol?
No. We use only the ethanol and.
Okay. And have you also considered using different types of oil types?
No. We use only sunflower oil.
Do you think using different types of
Yeah, of course, because its density and its dynamic viscosity, the surface tension of the liquid will change over time. No, not over.
Okay. And have you considered using other mixtures of water mixtures? For example, maybe water and soap.
What? Oh no.
Because I. And do you think that alcohol evaporates faster than water?
Pardon?
do you think alcohol evaporates faster than water?
Yes.
Okay. Okay. Do you think that as the radius expands, do you think its peripheral surface tension is greater than the inner surface tension?
Yes, the inner part has a lower surface tension, while the outer part has a higher surface tension.
Do you think that the alcohol concentration, or it's like alcohol concentration is greater on the outside or on the inner side of your droplet?
Droplet?
As it expands, yes.
As it expands, as I mentioned, the alcohol on the outer side evaporates faster than the inner side. So I think that can answer the question.
Okay, sure. And do you think that you should consider shear stress between the fluids, so your droplet and your oil?
No, we do not do that part. We don't think they will affect it.
I'm from the all-nighter team, and my name is Justin, and then I will be opposing the droplet explosion. Okay, and this is the problem statement. I'm not going to repeat it again, but then, okay, but for us, I think the opponent structure for solving the problem would be to actually discover the droplet fragmentation patterns and then the forces in play here, and then later on, because we have to determine the fragmentation properties, we have to determine its flow, velocity, and then also it's later on its maximum radius. And then at the same time, we also have to consider some of the critical conditions, determine some of the critical conditions, and then also some of the fluid mixture properties. Okay, and then to summarize some of the pros and cons the reporter did, he did show some of the phenomena concepts working, and he also determined some of the minimum concentration, the minimum alcohol concentration you need. And at the same time, he also pointed out that the surface tension gradient or the surface tension change is crucial to this phenomenon happening. However, in his slides, he has no really clear footage of the top or side view of the droplet actually expanding or decreasing in its length, in its height. At the same time, he also lacked various different parameters, such as different oil types and alcohol types, which he should have tested in his experiments. And then at the same time, while he only considered surface tension changes, he did not test for example, temperature changes, or at the same time, he also did not state how his initial conclusions, his initial conditions may have varied from trial to trial, or maybe he only did one trial for his data determining parts, for his data points, because he doesn't have error bars as well. At the same time, in his end, he doesn't have a real theory to account for the actual flow velocity, and also the later on determine the particle size or its maximum radius, basically for its critical conditions. Okay, and then talk about. Okay, so and also you mentioned that shear stress is a very you didn't consider shear stress in your equations, but don't you think that would affect the phenomenon?
Maybe, but we use only surface tension and we got the results. As for your mention, the tension, the force, I think the droplet is so small, and the oil. In our experiment, we did not consider that.
But I think shear stress will play a very important role here. Is it okay if I go draw before? Yeah. So let's say this is your drop. Let's say this is your droplet, okay, and then this is your water surface. But then, however, as you continue downwards, let's say your droplet becomes like this, and then so your droplet. So this portion is your droplet, okay, and then this is your oil. Okay. However, in between this, there's going to be some sort of friction in between. And that will be between this portion of the graph. Okay. And then that will be considered your shear stress. And then what that does is that may, I think, potentially deform your particle, and so that would reduce, that would affect its particle orientation. Sorry, your droplet orientation, and then change its potentially like its flow velocity outwards or its size in the end. Do you think that's true?
I agree that it will change the size of the mixture, but how do you think that if you add the force, how will the phenomenon change?
What do you mean by change the size of the mixture? The mixture is the same.
No, the big, like you say here, is like a low shape of the mixture. So I agree that the mixture's shape will change, but how will that affect?
Oh, okay. I mean, personally, I think this is something you should consider because it causes some deformations. For example, let's say if the particle expands this way and this way, as you continue on expanding, then wouldn't this be wouldn't this generate some deformation on the side to cause uneven spreads to the edges?
As for uneven changing, we did not consider this point, but yeah, as I said.
Okay, that's okay. That's okay. And at the same time, do you think temperature change would play a really important role in this situation?
We solved this problem, but we cannot Yes, maybe it will change, but we did some experiments from maybe 20 or so degrees from 30 or so, but it did not really influence it.
Okay. But then, so you think that potentially changing the temperature would affect these phenomena?
We did not see a significant change yet.
Oh, okay. But you consider that as a potential parameter you should consider?
Okay.
Okay, that's fine. And then it's okay to go to slide 14. 13 or 14. So for these, I understand that you plotted linear proportional between your Rmax and your concentration differences between, I think this is your alcohol. However, I don't see any error bars. Does that mean that you only did one trial?
No, we did this experiment various times.
So wouldn't there be deviations so that we wouldn't get in this case, like some sort of linear?
Okay, that's our error. So we only use one experiment data to draw this line here, so that's our error.
Okay. So do you think in future work you think something like adding error would be an improvement?
Yeah, of course. The adding error bar is quite important when it's running.
Okay, sure, that's fine. And then also let's talk about your experimental setup as well. So let's say your experimental setup, I think you did like a pipette and then you kind of drop one drop into water surface.
No, oil surface.
Sorry, oil surface.
Yeah,
something like that. Have you considered the point of your drop? For example, let's say you drop very, very low to the surface, or you drop very high to the surface. Did you ever make that constant?
No.
Do you think that will potentially change the rate of expansion and also the particles structure as land on the outer surface?
Okay. Yeah. Maybe it will change both the radius and the velocity. Maybe. We did not do this experimentally. But I think that if you drop at a higher point,
how would it potentially, like, would there be any deformations?
Deformation of the water mixture? Or
yeah, the water mixture. Yeah.
Yes, I do agree with that. Like, if the velocity of here is, of course, more than the
Okay, and then at the same time, you say that you drop from like tweezer or sorry, not tweezer, like a pipette kind of thing.
Yes.
Did you maintain the droplet's volume as a constant variable?
The droplet's volume. No.
Droplet's volume.
It's just a dropper, and we assume that each droplet is the same. And
do you assume they are the same?
Yes.
Okay. Do you think that there may be experimental variations?
Yes. It may be experimental variations. Yes, but we do not think that will hugely impact the phenomenon itself.
Oh, but for example, the problem statement is asking you to determine the final radius of your droplet size. Then, don't you think that by changing the droplet's volume initially, that would impact the final radius?
The final radius.
Yeah, something like that. Or also the fragmentation frequency. Okay. So for and then also, you stated in your own slides, you said that that alcohol, its concentration changes as it evaporates, right?
Yeah.
Okay. So let's say you made a mixture of alcohol and water. Don't you think that before the experiment was conducted, some of it already has evaporated and thus changing your initial concentration? So how did you maintain it to be constant?
First, in experimental methods, of course we want to do this as fast as possible, so that the alcohol does not evaporate that fast. But in reality, I know there will be some variances between the, like, say 80% between, there will be some errors. So I think in our future data we can just apply like what's the real proportions of water and alcohol mixture, like maybe 17:9 or so, and we.
But I'm asking for before your experiment was conducted. Don't you think that if let's say environment, wouldn't that change your initial measuring conditions, leading to more errors and deviations in your theory?
Okay. Yes, it may be influenced it.
Oh, okay. And then also, it seems like you don't have a full video of how the phenomenon is actually appearing. So how did you manage to like analyze and track its
so if this is the plate, okay, and we draw here. So we use a piece of paper on the oil, and we draw lines here. This is 1 centimeter, 2 centimeter, and we take off the paper, and then we can determine the radius and the velocity of it. Using tracker, we can say that if it radius like this, maybe it's
okay.
Yeah.
But then considering that the oil's color and also your droplets color would be, would you comment on that?
Okay. So we use two methods here. First, we dye it in red, okay, and so that the red color will be different from the yellow color. And the second one is we use a cell phone flashlight here, like the full screen is painted, it's shine maybe blue, okay, and then we put the plate on it.
Okay, I understand.
Yeah.
But then, however, I just realized, for example, if you change that, if you added food coloring, doesn't that also affect your initial concentration as well?
Yes, so I said we use this method and also this method. This method we do not dye it because the oil will be the
so your
same.
data is using this method?
Oh, no, these two things are in our experiment data is almost the same. So yeah, of course we use this one.
It's almost the same, but then you can't assume that things are the same if you change the initial conditions. You're not testing against other variables, right? So. Okay, that's okay. That's okay. And then also, it seems like in your presentation, you really never discussed the true purpose of the problem statement that asks you what to do. It seems like you didn't you didn't determine the actual final radius size of the particles, and also, for example, how many are fragmented, how many particle sizes, how many particles are there. Droplets.
We did investigate the radius of the inner part and the outer part, the radius here, and
but you have to consider that for this effect to happen, there's also expansions of droplets. It splits into different droplets, as you can see in the Marangoni effect. So then, for these droplets, each radius is different. So how did you account for these radius changes? Did you perhaps change it depending on its surface tension differences, or did you change it based on your concentration differences relative to your? Okay, so through our presentation, through our discussion, we considered various parameters that that report didn't discuss about. For example, things like shear stress, and also uneven spreading to the edges. There's also things like temperature change. At the same time, I also pointed out that the reporter did not include error bars for their concentration vs Rmax and Tn variables. And so this suggests that perhaps they didn't consider their accuracy of their experiments. At the same time, there's no experimental video on showcasing how it works. And at the same time, their presentation did not really address the main goals of the problem statement, which is to really determine each particle's radius based on your formulas, and then also how many fragmentations there are.
Okay, review some questions.
Okay, so I want to ask you answer one. So, will the coloring affect the liquid portion of liquid oil? I mean, if you have a portion of liquid oil and you add full color, and the B portion of oil and the water and add color, will
I think what you're asking is this one. If this like for example 70% of the alcohol, and we dye it in red, the result is the same as this the cell phone flashlight, and so the oil will become the same color as the cell phone. I think what you're asking is. Can you repeat this again? Oh, okay. So we place a cell phone here. Cell phone? Yeah. And if it's green, we download an app which can let the cell phone show the color like blue here, the both green, and so that the oil will be the same color here.
Can you show me your footage of the explosion of the liquid? Okay.
This one?
Oh yes.
So I think I can explain it. The inner radius will become greater, and then it will like become smaller.
Yeah. Go on. So I have a question for you. Do you guys try out different temperatures of the liquid that you drop down?
I'm not a reporter, so that I can't.
Also, what do you think the effect will be? What the result of the temperature?
Oh, I mean, for example, the most notable difference is that if you increase the temperature or decrease your temperature, things like your viscosity and also things like viscosity changes. And then at the same time, if you change the temperature in different locations, that will also affect its kinetic energy on different locations.
Explosion. And first, we can talk about reporter's review. The pros are clear explanation of the problem, clear relevant parameters mentioned, and mention the limit of the experiment, and they have a clear data. And the cons is not clear footage, and that affects, and we cannot clearly observe the phenomenon. And second, didn't consider enough liquid. As the opponent said, they didn't consider different kind of alcohol or oil. And third, the purpose of liquid use is not clear. For example, you can try a lot of alcohols that has different carbon chain length, and for not showing all the data. And the opponent review, the poses are good coverage. Second, good suggestion for the reporter. The contents are too much words on one side. And the point that they discussed is the liquid adhesiveness between the liquid drop and the bottom liquid. And the point the dropping drops. And this affects the shape of the explosion of the droplet. And third, the opponent asked the reporter about the sizes of each droplet. Will the size will be the same or different? And that is affecting factor for the result. And fourth, they discussed about the temperature. And this will affect also affect the radius and how big the droplet will explode. And fourth, the opponent questioned the reporter about the droplet solitude evenness, like the mixture between, if you are dropping a water and alcohol, and will the droplet that they drop even or not? And that's all for the review. Thank you.
I'm putting it now.
Okay. So during the discussion, first, the first point is the temperature. For a liquid, the temperature, if the temperature goes up, then the surface tension would decrease. However, I do not understand that what the opponent is really asking about the temperature, which part of the temperature. And second, the second point is the different volume of the droplet. Here, different volume of the droplet. Yes, we use dropper only, so maybe we can use more accurate thing like a pipette or something. And the height of the drop. We talk about if you drop it too high, then it may be sinking in the oil, so we cannot observe the phenomena, but it needs further experiments. And for shear friction, the part, shear friction, as the opponent mentions, we did not consider this part, but yes, we still need further experiments. And of the size of the droplets, there are so many droplets on the surface, and some droplets we cannot define it's really a droplet or not, so we did not consider this part. And so basically, we do need more experiments, but we think our experiment and data can show this phenomenon mostly, and that's the end of my remarks. Thank you.
Questions from the jury?
One question for you guys. Have you been considered just one small droplet and softly touch the oil surface, not from the height, right? Can it explode?
I do not did the experiment. So,
you can guess.
Okay. I think it will flow outward, but maybe its velocity will be lower than like from a higher position of dropping.
I think that if you just drop it on the closely on the surface, I think the radius of the total explosion will not be so aggressive, and you cannot see the whole phenomenon clearly.
Okay.
Can I draw some diagrams over here?
Sure.
And so let's say if you drop from near the water surface, what really creates the split in these drops is because of your difference in surface tension. And then since your alcohol evaporates faster than your water does, then that means your concentration changes as you go outwards. And then because of that concentration difference, that is the one that makes its mixture's surface tension different from its sides and its middle portion. So that creates this net change, which creates the actual droplet. So regardless if you put it on top or on the bottom near the surface, that shouldn't change. There will still be droplets happen, droplet fragmentations.
Okay, any other questions?
I have a question for our reporter. Can you go to page 13? Yes, this is your result. So is the line goes to your expectation value about 32% to form this arc?
Yeah, I mean, 32.74% is that the lowest.
Yeah. So I mean, does this line pass through?
Oh, you here?
Yes.
You mean here?
Yeah. What's the point here? Is it coincide with your prediction or numerical results? Do you
Yes,
check that?
I think so. Yeah, but we did not do this actually.
Okay. For opponent, you mentioned about the stress, right? The stress force. They didn't consider this. How about if you consider this parameter, does it change the line they draw here?
It shouldn't. It should only affect the flow rate outwards. But overall, it's a deformation, but it goes back to its sort of curvy droplet structure after a while. So it shouldn't change its R maximum trend. Maybe at the start a little bit, but then later on shouldn't change.
Okay. For reviewer, do you think what kind of parameter they can consider, including surface tension and stress, or only surface tension?
I think they can change the try different height or the potential energy from the droplet, because I think the fragmentation is caused by the potential energy when they are above the liquid that they drop now. So I think they should consider this, and they can see if the relationship between the height that the droplet drops and the different liquid, and they can consider, they can have make a new data about this.
You use oil and alcohol to conduct this experiment. Maybe I missed something here. Did you mention you get the same size of the final droplet?
You mean?
Or different size?
You mean the size of the outer here?
Yeah, final droplet.
Okay. I think the size of the outer is so small that sometimes I cannot even define which is a droplet and which is not. And no, we did not discover the size of the outer here, but we can see that this length. We can investigate this length.
Did you expect it will be equal or different size?
Oh, you mean? Oh no. As we see here, it's not equal. Like if like the outer and most outer.
And your opinion?
I think as you can see here, different particles have different radiuses, and then that radius depends on your concentration as you go outwards.
Your opinion.
I think they. I don't have any opinion. I think he did it very well.
Other financial guys. If you want to see more of these small droplets, what did you do in your experiment? You want to see more? Okay. Or I think sometimes it's a lot of sometimes it's all different stuff. Then the large. Okay. You want to see it's small and many small droplets. What did you do?
More small. If we want to like these are so small, maybe we can use a microscope. Yeah.
Okay. How about
to observe these small droplets, I think we can potentially change different oil types or different alcohol and water concentration mixtures, so that in general at the outer layers it will become either the radius will be bigger for generalization.
I think if you want to observe the smaller droplets, you can put a light source underneath the container, and maybe because of the coloring, you can see more clearly of where the little droplets go, like how big actually it is, because the coloring will make the position of the smaller droplets more obvious to see.
Okay, thank you. So let's start from the enclosure first. This way is yours. 7, 7, 6, 8, 7. Then opponent. 7, 8, 7, 8, 8. Then reviewer. Yes, please. 5, 6, 5, 5, 5. Okay, thank you. So, does anyone want to make some comment? Jerry? Okay, if not, so let's take a 10 minutes, okay? Let's take a 10 minutes break. So also move your chair first. Okay?